Got it. Let's try this. Did it work? Did it work? Oh, it so worked. Um, what's the button that I press? Okay. Hello, everybody. My name is Elliot, and I was asked to give a little bit of an overview of 3D mirror symmetry. Now, as Telamon pointed out, this is a big subject, and there's a lot of things that I don't really understand here, but I'm going to say them anyways, and people should yell at me if I say things wrong, and if they don't understand things I say, you should also yell at me. We have like 2 hours blocked out, and I'm just gonna kind of keep talking for however long it takes. So, yeah, please interrupt me. So my background in this, or sort of the thing that I'm presenting to you today, is this picture. So this picture was a picture I did on commission for Justin Hilburn, who's the author of some of the papers that we're going to be talking about. And he wanted an overview of mirror symmetry and in particular all of the other types of quantum field theories that sort of organize everything. And as you see, there's a lot of things in this picture. So I thought as a good way to introduce the notions of 3D mirror symmetry and the sort of structures that we'll be considering would be to kind of go through this picture and take a tour of what's going on here. Now, I know that Zoom kind of sucks for image quality. So what I'm going to do is I'm going to post a link to this picture in the chat. So if you want to follow along, then you can do so. And then we can all be happy with a nice, beautiful picture that's very big. Um, yes. Okay, where's the chat? Chat, chat, chat. There we go. Okay, are we ready? Um, what's going on? Great. Okay. So I guess part one, which is sort of the main part, is going to be about this physics framework. So let's make this bigger so we can actually see some stuff. And now, I mean, the philosophy of this talk is that physics is going to be our organizational principle. It's going to be the thing that tells us how the math parts fits together. And all of these different mathematical ideas will come from one theory up top that kind of rules them all, which is this one right here. 4D n equals 4 supersymmetric Yang-Mills theories. So let me explain just a little bit what these words mean. So 4D, this is going to be a quantum field theory. So it's going to be something which assigns, numbers or vector spaces or categories or whatnot to manifolds. And the 4D here indicates the dimension of the manifold that we're going to be putting in, the dimension of the source. So this is the source dimension. And this n equals 4 is an adjective describing this term, SUSY. SUSY is short for supersymmetric. And this is a thing that we can spend a whole semester talking about. In fact, we have in the past. I ran a semester on Coulomb branches at some point, but we spent a whole time just trying to understand what supersymmetry algebras were. So we're not going to go into it, but just to say a couple words, this kind of describes the symmetries of the algebra underlying the theory, and in particular, how the even and odd parts work together. So it's a measure of the amount of these symmetries. And Yang-Mills is an adjective describing the type of theories that we're going to be considering, which are gauge theories. So it's going to have to do with principal G bundles over some space with maybe some representations attached. And in fact, that's the data that we're going to start with. So our data is going to be a gauge group, G, and some representation of that gauge group. So we're going to call this, just for the physics words, this is the gauge group, as I already said, but we're going to think about this N as the matter content. Oh, and again, like we should think about these as words to try to translate what physicists are saying into our own language. Okay, so if we don't know what matter is, that's fine. But from this data, what we get is we get a quantum field theory. So together, these give us a quantum field theory, which I'm going to denote T. I'm going to put a little 4 up here so we remember how big it is. And it's going to take in a group and a number. Okay. And what does this quantum field theory do? Well, it's going to have a machine which assigns to any manifold or so forth a number. And we should think about this in the context of fully extended quantum field theories eventually. But that's a little tricky to do right now because right now this depends on metric. So really, we need both a manifold and some metric information on that manifold. And that's kind of no good for us because as mathematicians, we essentially have no clue how to work with quantum field theories with manifolds that have metrics. So what we need to do is find a way to turn this into a topological quantum field theory, which is the world that you all live in. And that's where this adjective supersymmetric comes in to save us. Because it turns out that if we have all of these supersymmetries, we can modify the theory in some way to remove all of the dependence on the metric. So what we can do is we can apply a topological twist. Well, let's make this bigger, sorry. And that will give us two different quantum field theories, which I will denote by the A twist and the B twist. Okay, now this is great. We get two separate quantum field theories from the same input data. Wouldn't it be wonderful if they were the same? And it turns out that's kind of what happens. So in these four-dimensional theories, so let me just give you some names. These two theories are called Kapustin-Witten theories, named after Kapustin and Witten, who first wrote these down. And we expect them to have a duality. That is, that for some G and N, which is to say that these come in pairs. Which means that for every G comma N, the data defining a theory, we expect there to be some sort of dual data, G shriek and N shriek, such that the A twist of the theory defined data G and N is isomorphic as topological quantum field theories to the B twist with data defined by the dual variables, and vice versa. So we're kind of swapping the A and B twists here. And this sort of phenomenon is what we call mirror symmetry. And that's what we're going to be kind of trying to track down is these two twists. We have up here, we have the A twist on one side and the B twist on the other. And there should be two mirror theories to one another that will give different equivalent ways of looking at the same mathematical information from completely different sides of the mathematical world. Now, we started in 4 dimensions because that's kind of where things come from, but it's not really where we can work because we don't really know how to do 40 TQFTs yet. So what we're going to do is we're going to take the dimension down. And that's what this tree is describing. So we have a couple of ways to, yeah. So let me just say, let's pull this picture in just so we have a nice picture of it. There we go. There's our two twists. And we expect there to be, yeah. We expect these to be things that come from categorical information, that come from, sorry, fully extended TQFTs. Which means that we don't have to feed it in a manifold of the same full dimension that the quantum field theory is considering. It means we can feed it in. That's what the Z means, is what I'm feeding into this quantum field theory. We can feed it in a point to get a free category. Except we don't know how to do this yet. This is hard. So we're going to try to dimensionally reduce in some ways. And the best way I know to dimensionally reduce something is to take boundary theories. Okay, so let's suppose that we have some n-dimensional TQFT, and we want to produce an n minus one dimensional TQFT, which is going to be the boundary. How can we do that? Well, what we need to do, let's draw a little schematic picture here, is we have our strip, which is, I'm thinking of my higher dimensional space as like I cross a lower dimensional manifold. That's my lower dimensional manifold down there. And when I apply my quantum field theory to this top thing, what I want to get is I want to be able to essentially integrate out this vertical direction. Okay? And that will result in a lower dimensional theory, which is the boundary theory. Now, to do that, I need to know what happens here at the top and here at the bottom. The boundaries are things where I need extra information, so we have to give them some labels. Let's say L0 and L1. Okay? So we need the data of boundary conditions to be able to define such boundary theory. Um, yeah, so in fact, the resulting lower dimensional theory should be some theory where the boundary has boundary conditions given by, in this case, L0 and an L1 of my original theory. Okay, so the boundary conditions are part of the data that define this theory. Now, in the framework of the cobordism hypothesis, or this fully extended TQFT language, we expect that the quantum field theory is completely determined by exactly the thing I was talking about earlier, its value assigned to a point, which is an n minus one category. And physicists call this category the category of boundary conditions. Okay, why is that? Well, it's because this is a category whose objects are the possible labelings that we're allowing earlier. So it's literally a category full of boundary conditions. L0 and L1, as our example from before says. And the morphisms between those objects are going to be, well, let's just take the Hom space, which remember, we're in an n minus one category, so this should be something that's an n minus two category. How do we get that? Well, we already described to you a way to get a lower dimensional TQFT schematically. So this is going to be whatever that lower dimensional TQFT assigns to a point, which in this case, because it's an n minus one dimensional TQFT, is an n minus two category. And now you can see how to induct this to get this sort of fully extended structure. Okay? So this is to say that the categories that we're thinking about, we should think about the objects as some type of boundary condition to our theory, locking in what happens as you walk to the edge of your space-time that you're thinking of your theory as living in. Okay, now starting with our Kapustin-Witten TQFT, we can sort of take these boundary conditions all the way down. So we're going to start with this four-dimensional theory, which is like a little draw like this sort of hypercube picture. And on here we have two twists. We have the A twist and we have the B twist. And we can take the boundary and get a three-dimensional theory, and then the boundary and get a two-dimensional theory, and the boundary and get a one-dimensional theory. Each of these have A twists and B twists, all of whom respect this boundary structure. Okay? And that's exactly what this picture right here is trying to show. This is the trunk of the mirror symmetry. Sorry, that's what I call this organizing framework. We can organize it like it's a tree. And at the very core is this sort of stack of quantum field theories related to each other by being boundaries of the one that are one higher dimension. Okay. I'm gonna pause a little bit here. Are we happy with boundary theories? Resounding yes. Wonderful. Now, there's another way that we could have chose to reduce the dimension, which is to actually do a dimensional reduction. Okay? And what does that mean? It means that instead of evaluating it on a strip where we need to know what's happening at the top and bottom, what we can do is we can evaluate it on a cylinder. Um, so we have our t-dimensional theory evaluated on a cylinder, and I can think about that cylinder as sort of living over a line. And whatever the t-dimensional theory evaluates on the cylinder, the reduced theory, that's n minus one dimensional, has to evaluate on this line. Okay? So this process of reducing quantum field theories by sort of adding in a circle is called dimensional reduction. And we should think about this as a separate axis of modification as the boundary theories. Okay, so here's the overall organizing picture. So we're going to have our four-dimensional theories up top, which remember are three categories. Then we have our three-dimensional theories, which are two categories. Then our 2D theories, which are one cats, and our 1D theories, which are zero cats. And our four-dimensional theories, as we said, we start with this sort of four-dimensional space, and then we reduce via a boundary theory to the three-dimensional space, and then again to the two and again to the one. So this is the same picture from earlier, where I'm taking boundary theories each time. And again, these two have two different topological twists. So I'm drawing in separate directions. Okay. But now we have a separate axis, which is what I just described, which is this sort of dimensional reduction, which goes diagonally, because this left axis is going to be our dimensionally reduced theories. So we take dimensional reduction, it sends our four-dimensional theory to a three-dimensional theory, which again has its own A and B twists. And then that goes to a two-dimensional theory, and then that to a one-dimensional theory. Let's do it again. Uh, Two-dimensional theory, one-dimensional theory. So how do we think about this? Well, this is our tree. And when we do this dimensional reduction, we lose information. We should think about this really as taking a shadow in some sense. And this is exactly how I drew it in the picture. So if we go back up, we see that there's this large tree on the left. Let's try this. Large tree on the left, and then the shadow below, which we achieve by taking a dimensional reduction. Okay? So back in this picture, we have the tree, we have its shadow, and we have its shadow's shadow. Okay. Now, this is where all of the mathematics of today lives. Or not of today, of what I'm going to talk about today will live. So I'm just going to write these things in about what objects live in which space. And this really is the map that you should consider when you're trying to think about how physics relate these different things together. So in the two-dimensional world, right here is where 2D mirror symmetry lives. Okay. And in one higher than that is 3D mirror symmetry. Okay. So 2D mirror symmetry is a boundary of 3D mirror symmetry. Now we can try going one below. If we take 2D mirror symmetry, take a boundary again, we should get a zero category when we put in a manifold. Which zero category do we get? And that's a vector space. And this basically, it turns out to be cohomology. On one side, it's Dolbeau, and the other side, it's de Rham. Let's even label all of that on these pictures. In 2D mirror symmetry, the B twist gives you the coherent sheaves, while the A twists give Lagrangians. We'll understand the 3D mirror symmetry side later. At the top, we have the Kapustin-Witten theory. which again, we don't really have much math for quite about now. Okay, what if we do dimensional reduction? Take 3D mirror symmetry, take its shadow, and we get to something called symplectic duality. Okay, this is a mathematical a consequence of 3D mirror symmetry that was discovered, in a sense, motivating this conjecture of 3D mirror symmetry. There's one more thing I want to put here, which is kind of why I put Kapustin-Witten in the first place. We could go from Kapustin-Witten and dimensionally reduce twice. And the theory that we get right down here is the one that gives us the geometric Langlands correspondence. And of course, we can like make this as detailed as we want. But this is the mind map of all of the things relating to 3D mirror symmetry. And today, I want to focus on sort of this corner of the picture. Okay? So before I get into more specific examples, does anybody have questions about this overall structure? Great. Okay, now we're doing less physics and more math, so maybe some people will be happy. What I want to talk about next is 2D mirror symmetry. Just as a quick review, because I'm assuming because Ping talked about this last time, but I want to show you how 2D symmetry fits into the language that we've been discussing all of this in the last 20 minutes. I don't need to write the title again. Okay. So what's going on here? Mhm. So let's just do this with a big flow chart. On one side, we have the B side. On the other side, we have the A side. Is this even a flow chart? So this is the type of twist of our theory that we're going to consider. And yeah, let me say that right now our theories are going to be theories that are defined by some Taylor manifold. So this is 2. So we're leaving this sort of notion that our theory is defined just by a group and a representation. And we're going to go to the more general case of what we call sigma models, where Z, when we take it and put it on some two-dimensional surface, is going to be some sort of count of the space of maps from the surface into M. Okay. Now, of course, there's many, many maps from a surface into M. So what this count means and exactly what type of maps we're considering is essential. And that's what the A and the B twist do, is they control which sort of maps you're looking at. So the B twist will look at locally constant maps, which in this case are just going to be constant maps, whereas the A twist is going to be looking at holomorphic maps. That is, we put some sort of complex structure on our surface. We already have a complex structure on our target because it's a Kähler manifold, and we're saying those two complex structures agree. Okay. So, as I just said, to understand the TQFTs in their fully extended sense, we have to understand boundary conditions. And we should think about these as manifolds of M, where we're demanding that the boundaries of sigma, so say these lines here, the boundary of sigma wants to lie on some subvariety or submanifold of M. Okay? So whatever sigma is going to do, it really wants to it has to have the boundaries living on something. Now, the difference between the A and the B twists is what the structure is on the submanifolds that it has to have the boundary living on. Okay? So the B twist is going to be holomorphic submanifolds. And if you want to like truly categorify this and be like Concevich, then you'd realize that the proper thing to consider is the coherent sheaves. In the A twist, you're going to have Lagrangian submanifolds. Okay. Now, from this structure of the type of submanifolds, we see that the B twist kind of sees the complex structure of the manifold, where the A twist is the symplectic side. It sees the symplectic structure. Okay. Um, how much do I care about that? Okay, the Hom spaces, let's just kind of put this into one, between two boundary conditions are going to be generated, but they're going to be, I mean, we have to do everything in derived, we have to get derived stuff out. So the Hom spaces, we want to think about this as some chain complex considered up to quasi-isomorphism. So we need some homology of some sort of complex. Okay. Now, in the B side case, this homology is going to be intersection points considered derivedly, which ends up, if you think about these as coherent sheaves, as just being the straight up homology of, um, or like the homology of the two sheaves with respect to one another. Whereas on the symplectic side, we get the intersection points. So the span of these, but where we're dividing out by the differential, which counts holomorphic maps. Yeah, we can see this in this picture here. So what's going on? We have our two-dimensional space-time that's getting mapped into our manifold M, Kähler manifold, via these branches. Now on the B side, the branches all go to a single point, and that point lives on the intersection of two of these holomorphic submanifolds. Okay? When you consider this derivedly, you get morphisms between coherent sheaves. Whereas on the A side, we have a map that gives us a two-dimensional surface, which we can think of as these little strings stretching between the boundaries of two different Lagrangian submanifolds. So we actually get contributions that sort of cancel out different intersection points from one another. That's an A-side phenomenon. Okay. And altogether, we have the statement of homological mirror symmetry, which is the fact that we can think about the category of these boundary conditions. And on the left side, it's the category of coherent on M, where on the right side, it's this Fukaya category of Lagrangian submanifolds, okay? And mirror symmetry posits, just like I said before, that a Kähler manifold M has a mirror pair, which I'm going to call M check. And what is this mirror pair? It's a mirror pair such that the underlying quantum field theories are isomorphic. The A and the B twists are related to one another. Okay. And because we know that we can understand a quantum field theory in terms of its category of boundary conditions, this is equivalent to telling us that the coherent sheaves on one side are equal to the Fukaya category on the other. Okay, that's classical homological mirror symmetry conjecture. Great. So let's just take this. I'm going to skip the 1D stuff because I think it's not so important. But let's just take this and try to play the same game in 3 dimensions. Understand the types of maps, the boundary conditions, the categories we want to associate to everything, and try to get some sort of mathematically precise conjecture, like this one, of what we expect the physics to say about 3-dimensional supersymmetric theories. Let's do it. That's part 2, 3D mirror symmetry. So whereas the quantum field theories underlying 2D mirror symmetry had Kähler manifold targets, The ones in 3D mirror symmetry will have will be one higher. Okay. So given a manifold M that is now holomorphic symplectic. No, let's say a better word. Let's say hyperkähler. And I'll explain what that means in a moment. Then we can define the twisted sigma models just as before, now in 3 dimensions. Okay. And these will be TQFTs. And what I'm going to try to do is describe what these TQFTs should look like. But first, what does hyperkähler mean? So that means M has free complex structures, which we'll call capital I, capital J, and capital K, such that they satisfy the only thing you could ever hope them to satisfy, which is that they fit together like the quaternions. So where a two-dimensional mirror symmetry dealt with complex things, three-dimensional mirror symmetry, we'll see again and again, deals with quaternionic things. Okay, so the tangent space is given some sort of quaternionic structure, but I said hyperkähler, and I guess I don't really need that, but let's just exculpate it a bit. That means that we have three compatible Kähler forms associated to each of these complex structures. Okay, and together this gives us a holomorphic symplectic structure. This is a thing that's weaker than hyperkähler because it doesn't have quite as much metric information. So the holomorphic symplectic structure, which is associated to complex structure I, will be given by omega j plus I omega k. And this is interesting because it is holomorphic with respect to the complex structure. Okay? This is a little exercise for you, I guess. Great. So this holomorphic symplectic structure is basically the only way we're going to be talking to this hyperkähler manifold. Kind of is pretty tricky to figure out what the hyperkähler structure is for a lot of these and to use it, but it's very interesting. But again, stuff for later. Okay, let's make the same flowchart. Okay, we have the B side, we have the A side. And the target, where in the last time the target could have been symplectic or complex, depending on the side. Here, we're always going to have M be hyperkähler. Let's put that right in the middle. Okay. And the thing of interest is, again, what type of maps are we allowing between our three-dimensional space and the hyperkähler manifold? So now our target space is our source is three-dimensional, and our manifold is this hyperkähler thing. And on the B side, we again have locally constant. Just like in 2D mirror symmetry. Oh, look at that. Whereas on the A side, instead of holomorphic things, we have things that respect the quaternionic structure. Which is to say, if we think of as R as the imaginary quaternions, H is what I'm going to use to denote quaternions, then we're saying that the quaternionic structure of this map is going to be preserved. And there's a fancy name for this, named after a person, which means it's hard to remember, but whatever. These are called feudor maps. So in 3D mirror symmetry, every time you would have been studying solutions to the Floer equations or the J holomorphic curve equations, now you're going to be studying solutions to the future equations. Oh boy. Okay, boundary conditions. both of them are going to be given by holomorphic Lagrangians, where holomorphic means that it's holomorphic with respect to, yeah. So these are holo Lagrangians. So what does that mean? Because it's weird because you want, like in ordinary symplectic geometry, Lagrangians can't be holomorphic. But remember, we have a holomorphic symplectic structure. So that is a submanifold L of M, which is complex with respect to our complex structure I, and Lagrangian with respect to what? With respect to the holomorphic symplectic form that is holomorphic with respect to I. Great. Okay. So now what it, pray tell, is the thing this assigns to a point. Okay, that's where we really want, that's what we really care about as people doing fully extended quantum field theories. So this is some sort of two category that wants to define these spaces. And I can't tell you what it is because in a sense nobody knows, but I can tell you what their names are because we've named them yet. We just haven't figured out what the names mean. Okay, so on the B side, we have the Rosansky-Witten two category. Which getting very close to defining. I think Bensby and Nadler gave a potential definition as their ICM address coming up this year. So, I mean, we're figuring this out. And on the other side, we have the holomorphic Fukaya category, something like that. Something that should work like that. But this is actually going to be a two category, so we'll give it a different name. A Futer two category. Okay? Which is a quaternionic analog of everything you do when you're doing floor theory. So great, we have successfully written down a wish list of what the yes of what the underlying quantum field theories in this 3D mirror symmetry world are, except for the fact that I haven't told you to target space. And that's kind of a big issue because you remember that we started this conversation by saying that everything was defined from a 4D theory with a group and a representation. And I don't see any groups and representations here yet. So let's try to figure out what those are. Now, to understand this, we're going to have to think a little bit more about the physics underlying things. So I guess what I want to say is that we want to be able to define some spaces, which I'll call MH and MC, living in the A and the B twist respectively, such that okay, sorry. I'm getting ahead of myself. Boop, 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 boop. So we defined a three-dimensional TQFT, which could have either A twists or B twists, which relied as an input a group and a representation N. Okay. Now what I described to you earlier was about sigma models. So we want to find some way to turn these into sigma models. And that is we want to build a hyperkähler space associated to G and N such that the quantum field theory will be identical to the quantum field theories I outlined above, applied to that particular space. Okay? Now, the way we're going to do this is using a vacuum, is using the moduli space of vacuum.
Sorry, Elliot.
Yes.
I think earlier you wrote T4 G comma N. So
Yes.
what kind of dimensional reduction is this
We've
related
done a
to?
boundary theory. This is the boundary of T4. And I haven't told you the boundary conditions that make this true because I don't know them.
Okay,
Is
thank
that
you.
good? Awesome. Okay. Moduli of vacua. So what is a vacua? A vacua is a physics word for some configuration of the fields underlying the theory of this quantum field theory, which has zero energy. Um, let me write a sentence that at least parses correctly. A vacuum is a configuration of fields that has zero energy. These fit together into what we call the moduli space of the vacua. Okay, so there's a lot of ways that locally, or there's a lot of ways that globally you can have a configuration of fields that has no energy and is perfectly okay. Okay, and these fit together into some moduli space. And why do we care about this? Well, because here's a very general thing that we can do to quantum field theories. Okay, so if we have our source, so right now we should think about this before we're topologically twisting. Um, so that we're going to remember the metric. Okay, so the source is going to be a small manifold. If we make our source be small, then it will embed into the space of fields, which is a very, very large dimensional space in some way. So if I have inside of my space of fields, we have some sort of space of the fields that have no energy, configurations that have no energy. These are the vacua. Then in general, we expect that the manifold will kind of embed all over, right? There'll be some quantum fuzziness. You'll have fields of all sorts of different energies. But there's a process in physics called renormalization, where you take your manifold and you make it really, really, really big. And as you make it big, these energy penalties for being off the zero energy state become much, much worse. So if instead we have a really big source, is math small or big? Who can say? If we have a really big source, then when this embeds in the space of fields, you know that it really can't leave the space of fields with zero energy at all. So we have this low energy approximation to our quantum field theory, which says that as things get really big, as the metric is large, it concentrates, or I guess it lives on the zero energy states. And any quantum field theory you start with will converge to a sigma model on the moduli of vacua. Schematically. Okay. Um, covering myself. But yeah, okay, it converges to a sigma model, right? So low energy theories, you can think about them as things which like only move along the space of zero energy configurations, which simplifies things greatly. Except we have one trick up our sleeves, which is the fact that once we've topologically twisted, these are topological. And what that means is it doesn't care about the metric at all. So we have this limit of changing the metric that simplifies the quantum field theory. But for a topological theory to begin with, we know that that didn't change anything. So the theory was already the simpler thing. So they are equivalent to scale limit. That is to say, we expect that these topologically twisted theories are going to be isomorphic to the theories that I described above with the target given by some moduli space of the vacua. Great. So now, like, in order to put things into this framework for our theory defined by G and N, we just have to understand what these moduli spaces look like. And luckily, they have names. It's good for things to have names because then we can talk about them. So the moduli spaces of vacua split into, let me just say, so first it has geometry. It's a hyperkähler manifold. And it has two irreducible components. We have the Coulomb branch. We have one thing that's called the Coulomb branch. I'll denote that MC. It's determined by G and N. And then we have a separate thing, which is some sort of other submanifold, which is the Higgs branch. So let's write this down. This is the Coulomb branch. And this is the Higgs branch. Okay. And the fun thing about these is that we can compute stuff about this TQFT using sigma models with either the Higgs branch or the Coulomb branch. But their underlying mathematics, like when you're actually sitting down, the fields of math that they talk about are this, like these are very different objects. And yet they can be used to compute the same things. So this suggests some sort of duality between the sigma models, and in particular, all of this information we learned about these things must be dual between the Higgs branch and the Coulomb branch. And this is the motto of 3D mirror symmetry. So let's write this down as an actual precise conjecture. When I'm saying precise, I mean precise in the physics words, okay? So conjecture, which is 3D mirror symmetry to a physicist. For a physicist. So we have a 3D TQFT, not a TQFT, just an ordinary quantum field theory, which has parameters given by the gauge group and some matter content. Let's be even more precise and tell you how much supersymmetry it has. Okay. Then there exists a mirror pair, a different TQFT defined by data, which is also some other group and some other representation, which I will denote by the shriek, such that what's this going for? Well, first off, we want their associated quantum field theories to be isomorphic to one another. So the A twist of one is the B twist of the other. And in particular, because the way that we're accessing these theories as mathematicians is to take their vacuum moduli spaces, these crazy manifolds of that these theories give us are also going to be dual. So the Coulomb branch and the Higgs branch are going to be interchanged, and vice versa. And that is what mirror symmetry looks like. It gives us two separate descriptions of identical quantum field theories. And these separate descriptions have a swapping between their Higgs branches and their Coulomb branches. Okay? You good? You happy? I'm not happy because I don't know what a quantum field theory is. So I want to sort of reframe this language into using this using these descriptions of these two categories, whatever they may be, I'm going to reframe this into something that looks a bit more like a math conjecture. Okay. So, like I said, we expect that we can identify these A and B twisted. From now on, I'm going to drop the free, but just know that there's going to be an invisible free every time I say it from now on. Okay. Okay. So there's the A and B twists are sort of defined by whatever they assign to a point, right? That's what which is a two category. And that's what the cobordism hypothesis tells us. And this is going to be one of these two categories associated to the sigma model with the target given by the vacuum moduli space, the Higgs bundle or the Coulomb branch, the Higgs branch or the Coulomb branch, right? So we're trying to look at these categories that we worked so hard to talk about and turn those into actual statements into actual 3D quantum field theories. Okay. So,
Is it is the video frozen for everybody? Yeah. Uh
I think the video is frozen. I don't know. I think I cannot hear anything.
let's see. So we are
I guess I thought that we should take a little break after an hour. And or I think I hit the escape button or something. I don't really know. How long ago did I drop off the face of the earth?
something like 1 or 2 minutes, I guess. Um
Okay. Oopsies. Did I say did I write this yet?
yeah, I think you basically was stopped before writing that line, but
Okay.
yeah.
Okay, let's just rewrite this line then. Okay. It's weird that what time is it? My iPad has forgotten how to tell the time. It's froze at 41 minutes. Daylight savings, I guess. Okay. The TQ of T assigns to a point the Rosonsky-Witten category of the moduli of Higgs bundles. Okay? I'm just tracing through the things I claimed were true earlier, but I also told you that this is equivalent to taking the B-twist of the thing with shrieked data, which we learned was given by the Rosonsky-Witten the B-twist now is given by the B-twisted sigma model, which is the Futer 2 category of the Higgs branch of shrieked data. And I told you that the Higgs and Coulomb branches were interchanged, so that should be the Futer category of the Coulomb branch with the same data. Okay. So this is, yeah, so whatever these are, whatever these categories are, whatever these spaces are, there should be a duality between them. Okay, let's write this as a conjecture, which is 3D mirror symmetry, 3B mirror symmetry, 3D mirror symmetry. For mathematician, which is that a holomorphic symplectic manifold, let's call it Y, if it happens to be equal to a Higgs branch of something, it has what we call a 3D mirror space. Just like two-dimensional manifolds can have mirror manifolds, this 3D mirror is going to be Y shriek, and it will equal the Coulomb branch of whatever theory it was that made Y the Higgs branch. Okay? Such that it will satisfy the following two interrelationships. The Rosonsky-Witten 2 category assigned to Y will equal the Futer 2 category assigned to Y shriek, Y mirror, and vice versa. I don't actually know how to spell Futer. I've been alternating EU and E. Um, and I'm sure that's fine. Okay. So that's nice. That's nice. That's satisfying. Like, we have a statement that looks a lot like 2D mirror symmetry, where we have two different manifolds whose associated two categories under either an A-side picture or a B-side picture will be interchanged when you take the mirror. That's awesome. Except for we have a little bit of a to-do list of things to understand. The first is to define a Higgs branch. The second is to define a Coulomb branch. It's essentially everything here. The third is to define the Rosonsky-Witten theory, and the fourth is to define the Futer 2 category. Okay, now let me tell you about the state of the art. Higgs branch is easy. Like, we know how to do this. We've known since the 80s. Coulomb branch is tricky, but there's a lot of work on it, and let's just say like Braverman, Finkelberg, Nakajima, 1, 2, gave the first mathematical definitions, etc. Telemon did some stuff with it. I don't know. But this is a thing that's recent, like 2016 and onwards. So we're just starting to understand what these spaces look like. The Rosonsky-Witten 2 category is like is not quite nailed down. And we have a proposal, I believe, for some spaces. We have a full proposal by Nadler and Benz-V. And their ICM this year, which hasn't happened yet. So this is like, this is coming. In the future category, there's a paper by Doan and Simone Reznikov, which proposes something, but we really don't know anything about it. We haven't done math with it yet. But this is still to do. Okay. So we have the spaces pretty well nailed down. Now the goal is to define the two categories we're working with, which is famously tricky, and to evaluate them on the spaces, and then we have some chance of comparing them to one another, improving mirror symmetry. But that is that's a story for a later generation, I guess. Okay. So this is the sort of broad overview of mirror symmetry. Now I'm told I have 2 hours. So what I would do now is I could either stop now if people want to get out of here, or I could start to give some examples of mirror manifolds and some of the more details on how to outline how to define these things for us to frame later talks. But either way, I'll pause for questions.
I had a question about above you said that this you take the sigma model where you take the whole moduli space of vacua
Mm-hmm.
or
Ah,
like
so
but
yeah,
then
sorry.
below it's you're saying that Z is something of a point is just the Xanthi-Witten of the Higgs branch or something. Why is it not the
Yeah, so this is a thing I'm a little bit unclear about myself. But yes, I said it should be a whole moduli space of vacua. But I think that the point is that you can't really move it from one branch to the other, right? Because they're different irreducible components. So if at any given place in your manifold you're living on one moduli space, then you're going to stay on that one. So now it's a question of like, okay, does it use the Higgs branch or does it use the Coulomb branch as your sigma model? And kind of the point of this whole duality is that it should give you the same thing. I don't know. So something like that. But yeah, I did do a little sleight of hand there, which you are correct to point out.
So I have a question if that's okay.
Mhm.
So one thing that confuses me when I learn about this is that sometimes people say, if I look at this 3D theory, let's call it C,
Mhm.
one of the twisted series, and I look at its value on S2,
Mhm.
kind of operators, then that's going to give me a E2 algebra, because
Yes.
the yeah, and one can somehow, because this is has some commutativity, one can take its spectrum,
Mhm.
and what one gets out of this spec of Z of S2 is going to be identified or maybe defined as the Higgs slash Coulomb. And
Yeah. That's
so
what I was going to talk about next. So
okay,
I can describe that.
I see. Right.
Okay. Um, very good. Very good, very good, very good. Um, great. So let's do that. I don't know. So I think that I will take a little bit of my sweet time, and I want to start by just t giving you exactly one example of these objects, just so you have a sense
Oh,
of kind of how to grab onto
Elliot,
them.
maybe wait a few minutes because I think maybe it's a good point to make some assignment now instead of 1 hour later since I have to run maybe 1 hour.
So
Yeah.
should I try to wrap up? How fast should I wrap up, Zechen?
No, I mean, I think we should do some organizational
Oh,
stuff
do
because
that
we
now.
plan to do this today. Yeah.
Now's a
We
good
need to do a
stopping
little
point.
bit like 5 minutes.
Yeah, why
Yeah,
don't we take a
and I can
small
get some water, so I'll go do
Yes,
that.
maybe now we could share your screen and then we
No, I'm back on Blaze. So let's stop being so abstract and start actually having something to say. Um, I think that'd be good. So let's talk about some examples. And the examples I'm going to give are like the canonical, like the good examples. These are the ones um that are always the first examples of Higgs and Coulomb branches. Okay. So what we're going to do is I'm going to follow in Ping's very large footsteps, and I'm going to describe the abelian theory, right? So just as Ping talked about toric mirror symmetry, I'm going to be talking about the analogous thing to toric mirror symmetry in 3D mirror symmetry. Okay. We're going to look at the abelian Higgs and Coulomb branches, which will turn out to be something called a hypertoric variety, just to give you the keyword. Um, picture. Hold on a second. Ah, okay. Um, yes. So what we're going to do is we're going to define the group G. So we're going to define a couple. Yeah. So remember, one of these theories is defined by a group and a representation. Okay. So our group is going to be U1, and our representation N is going to be a regular representation. So I'm being a little confusing here about regular versus quaternionic, but I'll try to disambiguate when it comes up. So, okay, I need to define an action. So for an angle theta, it's going to act on a tuple of complex numbers diagonally. Let's just write diagonally. And then we have the next example where G is U1 to the N. So an N torus acting on an N plus one dimensional complex space, where my action is going to be given by the one which is the standard action on the coordinate Z1 for Zn. And then on the first coordinate, it's going to be the thing that makes it all work. So negative the sum of angles, okay? So like, I mean, the details of what coordinates I'm choosing here aren't so important. I just want to be explicit so you know I'm not, like, it's not anything complicated, okay? So the Higgs branch of this first one is going to be a, sorry, that's inconsistent in my notes, but let me always write the correct thing. So this wants to be a quaternionic representation. Okay, so the Higgs branch is going to be a hyperkähler reduction. And let me tell you what that is. Okay, so first let me say why this is a quaternion. It's because T star of C, I should think of that as a four-dimensional space. What else is a four-dimensional space? The space of quaternions. So we can think about, if we choose some coordinates, we can think about T star of this as being n+1 copies of quaternions. And this has free complex structures given by the I, J, and K of the quaternions, just the standard ones. So this is a hyperkähler space. It's like just in the usual way, you know? Okay, so now we'll know it has an I, a J, and a K symplectic form. Now this U1 action is going to be Hamiltonian in all these symplectic forms. And when a U1 action is Hamiltonian, it means that it's generated by a Hamiltonian function. But because the symplectic forms are different, the Hamiltonian functions are different. So on omega I, omega j, and omega k, we have three different functions, mu I, mu j, and mu k, such that we have Hamilton's equations. So for any I, j, and k we put into this dot here, it's the same as the exterior derivative of this function is the same as contracting the symplectic form with that given I, j, and k by x, which is the generator of the U1 action. Great. Now we're going to organize these a little bit differently relative to the holomorphic symplectic structure we fixed at the beginning. So we will define mu I and mu C, which is a holomorphic function, which is mu J plus I mu K. That's a holomorphic thing. And you should think about this. Mu C is the moment map with respect to this holomorphic symplectic form omega I, okay? So now we can compute what's called the hyperkähler reduction, which takes, it's a crazy symbol. There's 4 slashes now. And why is that? Well, because this is defined by first taking a level set of the holomorphic moment map. So that's a holomorphic submanifold, right? And now we have our group acting on this thing. It preserves this. So we're going to take the symplectic reduction of that. Okay? Let me put this back. Yes. So we're going to take the symplectic reduction of this. And I've remembered this level set C. That's because I'm going to do... So if I just write this out, it's the preimage of this complex moment map intersected the level set of the ordinary moment map at this value C, all divided by U1. Okay, so why did I do 4 slashes here? Let's keep track of the dimension. This is dimension 4n+1. This part is dimension, we've just lost half of the dimensions because we have a, no, sorry. This loses 2 dimensions. This loses 1 dimension. So these two things in total lose 3 dimensions. And we've divided by u1, so in total we've lost 4 dimensions. So this is dimension 4n. So despite the fact we divided by a one-dimensional group, the dimension of the space dropped by a factor of 4, which is why we have 4 slashes here. Because in hyperkähler geometry, groups act 4 times. That's a lot of times. Okay. Now, what is the result of this? Yeah, so keep in mind that there's this parameter c, and that's going to be part of the data. Or you should think about the quantum field theory as having this extra parameter once you produce it that you can slide up and down and see how that changes things. Okay. Now the result, it turns out, is going to be is going to be something that looks a little bit like this. Oh yeah. Okay. So the result is that when c is not equal to 0, we get something that is the cotangent bundle of Pn. Okay, and to draw this picture, it looks kind of like a hyperboloid, maybe, with some central Pn factor. When c is equal to 0, we get something different. We get, oh, and this, by the way, yeah, sorry. The point of all this computation was that this is equal to the Higgs branch of this data. Okay. Now, when c is equal to 0, we instead get that the Higgs branch is equal to the space of n by n plus 1 by n plus 1 matrices such that the rank is less than or equal to 1, which looks something like this. This is a nilpotent cone. And the deformation you get of this nilpotent cone is going to be a non-singular variety, some sort of resolution of singularities, and this will in fact be the Springer resolution. And this is all in type, yeah, of type AN. Okay. So in this particular example, we ended up with this very nice picture that we recognize from representation theory, where we have a singular, non-singular thing that kind of contracts down onto the singular, onto a singular object when we change the stability parameters. And that's what this picture over here is representing. We can see the hyperboloids kind of contracting to a central cone. That's unreadable. It's the central cone, and we have the hyperboloids. Okay. Now, as I go down, let's take the other example. Okay, so we've figured out the Higgs branch. I've told you what the Higgs branch looks like for this particular group. Now let's do the mirror. So the Higgs branch for U1 to the N n plus 1. The Higgs branch is going to be given once again by a hyperkähler reduction. It turns out we're going to divide 4 times by this u1 to the n, and the result is going to be dimension 4. Because again, in hyperkähler geometry, groups act 4 times. And now we're going to have stability parameters for every single one of these u1 factors. Okay? And the result is going to be, topologically, it'll be a S1 bundle over R3 contracted over n points. Okay, so let me draw a little picture. We have our R3 here, and on top of that we have our S1 bundle, but at some points, it's going to the circle fiber will contract to a single point. Okay. And in particular, these points will be placed at the stability parameters that I defined earlier. Okay. Now, a better picture for this is to think of this as a chain of copies of P1 that are sort of lashed together at these points. And this will live over some base, which is, we should think of this as a moment map, C1 through Cn. And really, we want this total space to be some sort of cotangent bundle of a chain of spheres. Okay? Now, this whole space, this whole picture that I've drawn lives over a different picture. It lives over a singular variety, which is exactly the variety that you get when you contract all of these separate contraction points to a single point. So now we're dividing by just a bunch of zeros. Sorry, where our stability parameters are all going to be 0. And the result is something that looks kind of like, I don't really know how to draw this, but we have this like pretty nasty singularity here. And this whole space is isomorphic to C2 divided by the group action Z mod and Z. Okay? And this is the AN singularity. So this is pretty neato, because in general, we see that the Higgs branch for this particular data is going to be given by the unique resolution of singularities of this AN singularity. Let's write this properly. So we're resolving this singularity, and the exceptional fiber is exactly this map of spheres, this sort of chain of spheres up here. And these are arranged in the Dinkin diagram of AN, which looks like this. Okay? So this is just one instance of the McKay correspondence. And all of the other sort of resolutions of singularities also come up as Coulomb branches or Higgs branches of certain theories. And it's a very interesting way to approach this. So very rich McKay correspondence. Okay, so that's all I'm going to say about this. But now we have two nice pictures of what these Higgs branches look like. At least in the abelian case, they're all given by these hyperkähler reductions of linear spaces. That is, they're hypertorque varieties. And these two things are mirror to one another in the sense that the 3D mirror symmetry interchanges them. So the theory defined by U1 with respect to the first space, and the theory defined by U1 with respect to the second set of data. The Higgs branch, I just told you what they were. One of them was T star Pn, and the other was the resolution of singularities of C mod of C2 mod Zn. Okay. And these get interchanged when you look at the Coulomb branch. And this is a thing you can do explicitly if I actually tell you how to compute what a what a Coulomb branch is. But this swapping here is 3D mirror symmetry. And in the language that I described above, we have that the mirror manifold of the cotangent bundle of Pn is the resolution of the AN singularity. Great. What a wonderful example. Okay. What is that? Okay, let's just give myself a little more space. Um, so in general, and I'll say a little bit more about why this is true later, but the Higgs branch of one of these spaces is going to be given by the hyperkähler reduction of the quaternionic representation by G. And this is what I mean when I said it's easy. I mean, like, we can explicitly sit down and figure out what these things are. We can do the examples. In general, and these have the structure of these of what we saw, that there's a little bit more structure here. It's not just that we have a variety, we also have this way of contracting all of these exceptional fibers down to points. Okay. So we have a sort of resolution of singularities, which we expect to be somewhat generic. So let me define something for the first time in this talk, which is going to be sort of the thing that mirror symmetry has something to say about. Okay, this is called a symplectic resolution. X. And it consists of the following data. It's a smooth variety X with an associated holomorphic symplectic form. And this, a good picture to have is that of this sort of hyperboloid. It's our X. And it also has a singular affine variety X naught with resolution going from X to X naught. And that's this sort of double cone picture. Okay. So a symplectic resolution, the keyword symplectic is that we actually have a symplectic form up top, which sort of pushes down to a symplectic form everywhere except at the singularities. There's one more little bit of information that these have, which is a little hidden, but it's useful for getting structure out of this, which is that there's a scaling action of C star on this singular variety, which is to say that it's conical. Okay. Now, this is the sort of subject of 3D mirror symmetry. So 3D mirror symmetry, if we think about it, if we think about the objects that it has to deal with, it gives us a duality of symplectic resolutions. X and X check, okay? So we kind of have a sense of what these look like and kind of the math, the geometry that underlies them. So I'll pause here for questions before moving on to the question of observables and actually defining the Coulomb branch.
Can I
Okay.
ask a question, Elliot?
Yes, please.
So you have this parameter C. This is kind of a real thing, right? You have maybe in the first example, you have like a roughly an hour's worth of choices.
Mhm.
Um, what's my question? Like if I was like if I only knew about algebraic geometry, which I do, um, I might want to say I'm just gonna take a hollow like just a simple, let's say like a reduction by taking some moment map value for I guess mu I and then the mu c and then quotienting or something along those lines.
Yeah.
And I think that gives me like a complex number value,
No,
complex
so
numbers worth of parameters.
there's actually one more. So mu c is a complex valued function. So mu
Uh-huh.
c is a complex number, mu I gives you a real number. I
Uh-huh.
chose take mu c to be 0.
Uh-huh.
I don't think you have to, but I think this is kind of most common, at least
Uh-huh.
in the abelian case, this gives you everything you need.
Uh-huh.
But again, maybe if you're uncomfortable with the fact that I have told you to think about a real number when you're doing algebraic
Yeah.
geometry, think
Uh-huh.
about this as a stability parameter for a GIT quotient, because that's
Uh-huh.
exactly what it is. So instead of doing, let me just say this differently. So instead of doing this whole construction, instead we can take mu c inverse of 0, which is a actual variety.
Right.
We can take the functions on it and then take the g invariant functions. Now we have to complexify g for this to make sense, but we'll do that. And then
Uh-huh.
and what I've just told you is to take the affine GIT quotient of mu
Uh-huh.
e inverse of 0 mod g
Uh-huh.
c. But that's only the affine GIT quotient. If I want a projective GIT quotient, then I have to have some parameter here, and
Right.
that's what
And
this
this
is.
parameter will be complex and not real.
No, it'll be in GIT, it's still a real parameter.
Oh, it's still real. Oh, okay, okay.
I mean, for U1 action, or it would
Oh,
be something that
oh,
lives in U1, maybe. I don't remember, but it's
oh.
yeah,
Okay. Then maybe I'm happy. Good.
okay,
Thank you.
awesome. Great. So let's actually talk about Coulomb branches. And let's try to address the question about like what's this deal with spec of S of something or other. I don't know what that's going on there. Okay. Where was I? Where was I? That's where I was. Okay. So big new, what is a Coulomb branch? So I mean, I told you how to make Higgs branches, but we need to be able to construct the mirror variety, which is to construct the Coulomb branch. And the way we're going to access this is we're going to be nice to Yuji, and we're going to think like algebraic geometers. Which is to say that we will identify the Coulomb branch as the spectrum of the ring of functions on the Coulomb branch. That is to say, it's an affine space, which is okay because I made this affine assumption up here. Um, so yes. So how do we access the space of functions? Well, what we need to do is we need a way away from physics to produce a function on the Coulomb branch moduli of vacua. So what does that mean? I need a thing that takes in a vacuum configuration, a vacuum field configuration, and it needs to kind of, what happened there? Take this in and it needs to output a number. Okay. How do we do that? This is an observable in physics words. Another way to say it is we will measure the value of an operator. Okay. And we're going to do that. We're going to access our operators via a philosophy called the state operator correspondence. Okay, what does that mean? So what that means is uh, we're going to think about what Z of S2 looks like. This is going to be some Hilbert space. And it's going to be, we're going to think about this as the Hilbert space of points. Sorry, excuse me, of states living at a point. That doesn't make any sense. Of states on S2. Okay. There we go. But every state on S2 will give us an operator. In other words, some way of taking in some pre-existing TQ of T configuration and outputting a real number. Okay, so we're going to take any free manifold M, which is going to have sort of any sorts of structures that we want on it. It could have boundaries, as long as those boundaries are labeled. It can have this and that and the other thing. But we're going to excise a ball. Okay? And this, because of the ATIA definition, this gives a cobordism. Okay, sorry. Excising a ball gives a cobordism, and the ATIA definition lets us translate that into something else. So we're going to take our free manifold, we're going to cut out a little ball. So now we have a new part of the boundary, which is S2. And this is going to be some map from Z of the boundary of the free manifold into the old boundary into the new boundary, which is going to be S2. But recall, we've added a bunch of decorations to make sure that this will be evaluated as a number. So this image is going to be a number. Okay, this image is going to be a vector. And then we're going to pair this with V, which is our vector inside of this, our state. And we're going to get a number. So we should think about this as evaluating a point operator. We have something that's something like a monopole or something that lives in a single point. We're going to cut out a ball around it, and we're going to realize the modification obtained by that operator as just some vector on this new boundary component that we've produced. Okay, that's the state operator correspondence. It's immediate from the ATIA definition of TQFTs. So here's my little picture of this. Up, come on. So we see that our operators in this case are going to be these fun little acorns, and they're living in their little circles, okay? But this gives us an opportunity to take products of operators, which is to say that we can consider what the TQFT will assign to replacing two operators close together with a third operator. That's the multiplication of the two, okay? So we have a ball where we excise from it two smaller balls, and the result will be a map from Z of S2, tensor Z of S2, into, so those are the two inside ones. Maybe I'll label them, I'll color code them. And it'll map to the outside Z of S2, okay? And what we have here is a product, an operator product. So great, that's the E2 algebra that Longman was telling us about, which is to say that every 3D TQFT gives us an E2 algebra. Awesome. And it's commutative. That's what E2 means, or that's part of what E2 means, because if I have my red and I have my blue, then I could just take my red and I can just slide it past my blue, and I can get a new thing which looks like this. So I can just swap the order without changing anything in the topology, so it's a commutative thing, okay? So that's this product structure that we see here of these little acorns. Now, what we're going to do is we're going to realize that each of these operators, so every vector inside of this Hilbert space, each of these operators gives us a function on the Coulomb branch, okay? Now, I guess this requires a little bit more physics belief to believe in it physically, but I guess what I'm saying is each point in the Coulomb branch is some configuration of fields. Each of these things is an operator. We can take our field, excise a small ball, add in a new thing, which is that vector V, and see what the resulting number is. That gives a function. Every vacua gives a potentially different value for this operator. And the insight is that these are going to be all the functions. So this gives us the definition that we need. Is this right? So yeah, I like it. Yeah, okay. These are all of the functions. So the Coulomb branch, the way we get this is we take the spectrum of whatever the algebra of operators of the A side theory is. And this I'm going to denote by the algebra sub A. Whereas the Higgs branch is going to be the spectrum of the operators of whatever the side theory is. And we'll call that the space of operators. So these are the algebras of operators. Okay, great. So if we understand our TQFT structure, then we don't need to worry about whatever vacuum means or anything like that. From our TQFT structure, we can extract the vacuum moduli spaces that we're interested in. So let me describe to you in some more detail how to actually produce these algebras and what the associated spaces look like. But before I move on, any questions about like why this construction makes sense physically? You happy?
So you seem to be making the not so much trivial physical claim that all the functions on this MC is going to be detected or keep constructed by taking the expectation value of a point operator.
Yeah.
Okay.
I don't have more to say. That's what must be true given what people tell me, that this is the spectrum. There
All
are
right.
line operators. Those also give functions. I don't know. Maybe it's that the Higgs and Coulomb branches are exactly the parts of the vacua that you can like see via point operators somehow, but I don't know. If anyone else can save me, I'd be happy to hear. Was there a chat message? Did someone ask something in chat? Where'd it go? Okay. No. Okay, so let's actually work out these rings of operators a little bit. Okay. Now to do this, I'm going to have to tell you about I'm going to have to just say I'm going to just have to say by fiat how these quantum field theories work, but that's okay. We're going to make a simplifying assumption, which I guess I've been implicit in this whole time, but we're going to assume that the quaternionic representation that we started with, so now what I'm going to do is I'm going to do another sleight of hand, is I'm going to denote the fact that our group is actually going to be the complex group. Because earlier I was working with the compact group, I've been kind of trading between them. But every time I write G sub C, that means complex group. Every time I just write G, it probably also means complex group, and I forgot to put it, at least from now on. Anyway. The quaternionic rep is of the form, the cotangent bundle of of a complex rep. Okay, so by taking a cotangent bundle of a complex vector space, you can get a quaternionic vector space, which is kind of an amazing fact. Um, so what we want to do then is this makes life a lot easier. So we expect that. Oh, what do we expect? Okay, let's give us some more space. We expect that the whatever we assign to S2 should be okay. What if, now I'm going to say something which is again part of the physical sort of system of belief. It should be a one-dimensional quantization of the moduli space of maps, which is some infinite dimensional space. Okay, so it should be a geometric quantization of a space of admissible maps from S2 to, well, the target. And in this case, the target is going to be, because of this simplifying assumption, it's going to be the Stacky quotient of your complex rep divided by your complex group. Okay. Now, this word admissible is once again doing a lot of heavy lifting. Hiding inside of this is some sort of supersymmetric localization argument that tells us that this will actually end up only being a finite dimensional space of maps when we're actually examining it, so we can actually geometrically quantize it in a reasonable way. Okay. Great. So what is that going to be? Well, let's think about S2 in a different way. As it's going to be, well, we're going to take R3, we're going to cut out the origin, we're going to identify along vertical lines. This is sort of a perspective of, I guess that's reasonable in TQFT. If I think about like my horizontal slices as my spatial slices, and as I'm moving through time, most of the times things are just going to be identified with one another. But if I happen to hit the operator, then there's going to be some sort of discontinuous change. So I guess what I'm claiming here is that the natural topology of S2 is not actually the topology of S2, but instead it's something you get by taking this cylinder and smooshing along the edges like you're making a raviolo. Hence we have this space, the raviolo. Mathematically, it's described by a disjoint union of two disks, the top and the bottom disks, where we quotient them out by the equivalence gluing along the disk with the origin missing, which is d minus 0. Okay. So this is also, we can think about this as a complex line with two origins. So it does not have a Hausdorff topology. And here's my little picture of the raviolo. Let's put you in. Come on, come on. Oh, let's make more space. There it is. Our acorn is pulling together the space around it and is ended up trapped in the ravioli. Apparently, when 3D mirror symmetry was taking off, it became very awkward to just refer to the space as two disks glued along a formal disk or something like that. So everybody got together and it's like, okay, we need a good name for this. And there's this conversation where some person said, oh, I think it should be the Frisbee space. Another person said it should be the UFO space. Somebody suggested the ravioli space, which was wonderful for everybody except the Italian, who got very mad that they used the plural form ravioli instead of the singular form raviolo. That's where this name came from. All right, now, what is the algebra operators then? It's going to be some sort of quantization, some sort of ring of functions on the space of admissible maps. Now, what is the space of admissible maps? Let's scroll way up to remember that on the B side, the admissible maps are things that are locally constant. Whereas on the A side, they're things that are holomorphic, roughly. That's true uniformly. Like the thing that we're seeing all over the place is that whenever you go between the B and the A side, the thing that you swap is the word locally constant for holomorphic. If you'd like, maybe in Ping's talk, that was the coherent constructible correspondence was the two sides of mirror symmetry. But okay, way down here again. So we have the B side, which is going to be, let's make this smaller, which is going to be the space of holomorphic functions on the space of locally constant constant maps from the raviolo to the stacky quotient. So hollow maps, hollow functions, locally constant maps. In contrast, we have the A side, which is the space of locally constant functions on, I haven't told you what that means yet, but morally, it's locally constant functions on the holomorphic maps from the raviolo to the stacky quotient. Okay, and this line is the mirror line. 10 minutes, I can do this. Okay, so let's talk about, again, the B side first, because it's always easiest. The Higgs branch is the spectrum of this B-side algebra, which was going to be, well, I just told you it's the space of holomorphic functions. So the spectrum of this, it's just going to be the underlying space. It's just going to be the maps that are locally constant from the raviolo to the Stacky quotient. Okay? Now, we have a different way of describing this, which is to say that I need to charge my Apple Pencil. Okay. Any questions?
Why is it the Higgs branch here?
Huh?
Why is it the Higgs branch that is being computed?
Higgs branch is B-side. I said that up at the top. I told you that the Higgs branch was the algebra of the B-twisted theory. This is just part of the definition.
Oh,
So that's a
okay.
distinction branch. And maybe that's a better answer to Swapnil's question about why I took Higgs branches earlier. Okay, I have 10 more minutes to talk, so I probably only have to plug in my pencil for like that long, and it should be okay. Great. So the Higgs branch is the spectrum of the B side. So how do I describe this? Well, it's going to be a point because it's a constant map. It's going to be a point on n mod GC, and it's also going to be and a covector at that point. No, I don't really have a good answer for this. I think the answer is that the schematics only go so far, and at some point you actually have to do some derived geometry. But I think this covector thing is sort of remembering the orientation of the disk, because we do have this sort of infinitesimal structure, despite the fact that it's locally constant. I have the direction that it's being pinched. It's kind of how I think about it. Anyway. So, blah, blah, blah. What does that mean? What that means is that this is going to be the cotangent bundle of this quotient. And it turns out that that's going to be the symplectic reduction of the cotangent bundle by GC. Now, what does GC mean? Well, we have to like, if we want to turn this, yeah, and this, we have to remove the complexness from the bottom. If we want to do that, then we have to take it as a hyperkähler quotient. But maybe a more natural way to say this is that the algebra of operators is just going to be the functions on the inverse, this holomorphic. Why is it so big? It's going to be, the algebra of functions is going to be just all the functions on the inverse of 0 and then the G invariant part, which is what I was telling you earlier. So that's why these two are the same. So just from this perspective, we can see why the Higgs branch is in fact a hyperkähler quotient, and that's very nice, and that makes us happy. Let's talk about the Coulomb branch. Coulomb branch, Coulomb branch. Whoop. To do this, we're going to have to think formally. So we should think of the disk as the spectrum of the power series, the Taylor series, and the punctured disk as the spectrum of the Laurent series. Okay. Now the maps from the union of two disks modulo the punctured disk into n mod g, we can describe them as given by the following data. We're going to have maps n plus or minus from D to your representation space. And we're going to have a gauge transform G plus or minus. Oh, let's be more careful about this. N plus and n minus are two different maps. Then we have to glue them together everywhere except for the center. So we have G plus or minus from the formal disk to the space of transforms, of symmetries, of the gauge transforms. And then this is going to be up to overall transforms from the disk to the group. So we have a section on the top, a section on the bottom, we're modding out by and a thing that glues them together, and we're modding out by retrivializations of the top and retrivializations of the bottom. It's essentially the space of principal bundles on this raviolo. Okay, so let's write this algebraically. So the space of maps that are holomorphic from this raviolo to the stack and mod G is going to be given by, well, we have our maps from the top disk to bottom disks and the gluing, which satisfy that the top and the bottom maps are going to be Laurent series in N. The Taylor series in N. The gluing is Laurent series in G. And they're going to glue to one another. Which is, so we're gonna have this gauge transform property. Let's give us some more space. Make it smaller. We don't need to see this. Okay. And now we have this set, and now we have to divide out by the power series in G on the left, and on the right by exactly the action of multiplication. So the left action says that H plus times this whole tuple. What it's going to do is it's going to act on just the top part, but now we have to get the gluing to work, so we're going to have to multiply the gluing function too to make sure it works out. And then the right action is going to be defined similarly. H minus N minus, let's reorder those. I guess, no, I shouldn't. And then G plus minus H minus inverse, probably. Okay. And all together, we have this space which is called the BFN space, I believe. G and N. And what is this? Well, this part right here, I'm going to call this Z sub G comma N. This is some sort of like affine Grassmannian looking thing. If we set N to be 0, it is literally the affine Grassmannian, I think. And then this says up to equivariant action. So we're going to look at it with a group symmetry on it. This is the sort of double coset description, okay? And now what does locally constant mean? Well, locally constant means Borel-Moore in this case. That turns out that's the right word. So Borel-Moore homology. So in total, the Coulomb branch from this description should be the thing whose ring of functions is the Borel-Moore homology of the stack equotient of this BFN space by the symmetries. So the space of, this is the constant functions on the space of maps. But just to rewrite this one more time, the way we understand homology of stack equotients is to do equivariant homology. So we have the equivariant Borel-Moore homology applied to this affine Grassmannian looking space. And this is our standard picture for the Coulomb branch. And I guess in the rest of this seminar, we're going to understand this in actually some detail. And I don't know, talk about the Rosonsky-Witten category on it or something like that. Okay, that's all I have for you. Oh, I guess I want to point out here's our little homology squirrels. They're the things that measure homology. They're taking our little observables and they're rolling them into, I guess this should be N mod G, and they're measuring the homology of that, and that gives us our Coulomb branch. And altogether, that is all parts of the mirror symmetry, at least before taking the shadow. Thank you very much.
Thank you. Yeah, so this is 2 hours, so please feel free to leave. And if you have questions for the speaker, you can